Okay, so good afternoon, everybody, to this session at the ICM, at the virtual ICM. We have a prominent first speaker in this session, Alessandro Giuliani from Rome. Alessandro is well known for his substantial work on many-body systems, quantum systems, renormalization, but also other, and we will get to know, in fact, classical statistical mechanics results today. And let me now pass on the word to Alessandro. But before, let me remind you that there is no session for asking questions after the talk. So those that have questions are please asked to go to the Discord room and post the question there in the chat. So now, Alessandro, please, the floor is yours.
Okay, thank you very much. Thanks a lot to the organizers for the invitation. It's really an honor to be here today and have the opportunity to present my results. So I will review some results on universality of scale limits of two-dimensional non-integrable Ising and diamond models. For time constraints, I will mostly focus on the part on diamond models, which is based on joint works with Mastropietro, Toninelli, and more recently also with Bruno Renzi, and also based this latest part on several fruitful discussions with Benoît Laslier. The Ising part, I will just touch it tangentially, is based on a series of joint works, mainly with Mastropietro and Greenblatt. So an important concept in this talk is universality in the context of equilibrium statistical mechanics that roughly speaking, refers to the robustness of the macroscopic behavior of an interacting many-body system with respect to the details of the model used to describe microscopic interactions among the elementary constituents of the system. So this concept or principle is basic, I would say foundational for statistical mechanics, in that essentially, inevitably, due to the complexity of the systems we want to describe, any model we can write down and study is necessarily an oversimplification of reality. So for instance, if you study models for a magnet, you may consider Ising or Heisenberg models. In the best case, you would include some effects from quantum mechanics, maybe some effects from disorder, but whatever you can write down will be extremely simpler than what really takes place at the microscopic scale in a real metal or magnet. So in order for statistical mechanics to be predictive, we need that at macroscopic level, what we compute is largely independent of the details of the model used to describe the system. And this is vaguely the content of the universality principle. This concept is particularly subtle and deep at or very close to a critical point, where typically at a critical point corresponding to a second-order phase transition or a continuous phase transition, where typically correlations among fluctuations of local variables decay algebraically at large distances, rather than exponentially, as it's usually the case away from the critical point. In situations where correlations decay so slowly at large distances, central limit theorem, for instance, is not applicable, and it's unclear what are the techniques to prove existence of the scale limit and possibly prove that it exists and is non-Gaussian in interesting cases. So one of the great conceptual successes of statistical mechanics in the 20th century is the Wilsonian renormalization group, which provides the right framework for studying exactly these questions. at the coarse level, Wilsonian renormalization group provides an algorithm for computing the critical temperature and the macroscopic theory. It consists essentially in defining a map from the original Gibbs measure e to the minus beta h to a new effective one, e to the minus beta prime h prime, obtained by integrating out the small scale degrees of freedom and rescaling. And this map defines a map for the effective temperature and the effective Hamiltonian. And the game somehow is to choose the appropriate value of the inverse temperature beta c, so that this iteration of this map for the effective Hamiltonian converge to a fixed point. And this fixed point, when it exists, typically is a scale invariant Euclidean field theory that, under some mild additional locality assumptions, is supposed to be conformally invariant. So this scheme is widely accepted, considered conceptually correct, and has been used to really compute numbers in many non-trivial systems. But it's very hard to give mathematical foundations to this scheme and really use it to prove universality in explicit classes of microscopic Hamiltonians without neglecting a priori certain infinitely many terms, which is usually the case. So the challenge is to do something of this sort, particularly in situations where the scale limit is supposed to be non-Gaussian, which is the most interesting situation. In this setting, the non-rigorous results are mostly limited to 2 dimensions, and I will consider 2 dimensions only in this talk. And the strongest results you obtain concern Ising and Dimer models. So these are models that in their standard formulation on a planar lattice are exactly solvable, and they're exactly solvable in a very strong sense. The solution exhibits a determinant structure that can be interpreted as an exact mapping of the standard planar system into a gas of free fermions. And once you have this mapping, you can relatively easily compute the bulk scale limit of certain specific observable correlations, in particular those that are local in the fermionic representation. So the standard classical solutions of Ising and Dimer, due to Onsager and Castellan, have been largely extended over the years. And in recent years, in these settings, universality of the scale limit has been proven in different and complementary senses. So in the sense of geometric perturbations of the domain where we live, and of the underlying lattice on which the model is defined. And here, roughly speaking, the methods involved are based on discrete holomorphicity. And with respect to perturbations of the microscopic Hamiltonian defining the model. And this kind of perturbations are typically treated via constructive fermionic renormalization group, even if not exclusively. So here is an incomplete list of contributors and of main results obtained in the 2 settings. So in the setting of nearest neighbor planar Ising and Dimer models in domains of arbitrary shape with underlying lattice much more general typically than the standard square or hexagonal lattice. Results include construction of the scale limit of spin and energy correlations and of interfaces as far as the Ising model is concerned. Scaling limit and massless Gaussian free field nature of the scale limit for height correlations in Dimer models. And for both classes of systems, conformal covariance of the limit with respect to Riemann mapping of the domain we are considering into other domains, and universality with respect to a large choice of underlying lattices. In the context of interacting or weakly non-planar case, in which typically the model is non-solvable, but the geometry, the restrictions of geometry are more severe, main results include the construction of the scale limit of energy correlations in specific geometries like plane, half plane, torus, and cylinder, computation of the universal subleading corrections to critical free energy, and for the dimers, Gaussian free field scale limit of height correlations and universal scaling relations between critical exponents. So in this talk, I will mostly focus on these last two items, and which has some certain distinctive features compared to the results obtained on Ising models. So Ising and dimer models at the technical level share a lot of common features, but there are also some important differences that I would like to stress here. So Wilsonian renormalization group in particular predicts that weak short-range perturbations of the standard planar solvable models are irrelevant for Ising and marginal for dimers, as well as for other models that can be formulated as coupled pairs of Ising layers, such as Ashkin-Teller, 8-vertex, and 6-vertex. So irrelevant here means that at the dimensional level, you can prove relatively easily that an appropriately averaged form of the interaction at large scales scale to zero as the scale tends to infinity. Marginal means that at the dimensional level, you cannot exclude that these appropriately rescaled averages diverge logarithmically. So if you don't have logarithmic divergence, but rather boundedness of the effective interaction, you need cancellations. And in this context, interacting dimers or Ashkin-Teller, etc., cancellations are due to the so-called property of vanishing of beta function, which allows one to prove that not only doesn't grow this effective interaction at large scales, but tends to a constant that is comparable with the strength of the original perturbation in the Bayer model somehow. And this fact that the interaction effects don't scale to zero at large distances implies that in general, the interacting model, the perturbed model, is characterized by critical exponents that change continuously with the strength of the perturbation. So if you have some notion of universality for these systems, this notion of universality is not the naive one that all critical exponents remain the same, as is expected in Ising. Right notion is due to Kadanoff, who called this weak universality. The model in general is characterized by several non-trivial exponents depending continuously on the strength of the perturbation, but all of them can be reduced to the computation of just one of them via simple universal scaling relations, saying that, say, one exponent is the inverse of the other, another exponent is 1 over 2 minus the first exponent, and so on. So this single exponent that is needed to reconstruct all the others plays the role, if you like, of the parameter measuring the distance from the free Fermi point or the strength of the perturbation. So in this talk, I would like to review selected results of this sort, in particular on weak universality, for weakly non-planar dimer models, in a setting that was motivated by a question posed some years ago by Scott Sheffield in a workshop on dimers. And in brief, the setting and results are the following. So we consider perturbations of the standard planar dimer models due to additional non-planar edges with small weight. These additional non-planar edges are defined in such a way that you have space among them that as much that you can define height difference between appropriate phases via lattice paths that avoid to pass under these non-planar edges. So there is a notion, well-defined notion of height even for these non-planar models. And for this well-defined notion of height, we study large-scale behavior. We prove convergence to a Gaussian free field with a stiffness coefficient in front that is related to via an exact scaling relation to the anomalous dimer-dimer critical exponent. So the resulting picture is compatible with what formal bosonization predicts, even though we don't use bosonization within the proof. So now that the overview of where I want to get to should be relatively clear, I hope. Let me go to a more precise definition of the model. And before that, a very brief recap of some basic properties of dimers. So to recap of some basic properties of dimers. So two-dimensional dimer models are highly simplified models of dense liquids of anisotropic molecules, or equivalently, if you are at close packing of random surfaces. So here is a picture. On the right, you see a typical dimer configuration at maximal packing. Here, the dimers are these sticks of length 1 that you can arrange on the lattice with the condition that no pair of them can touch. So there is a hardcore repulsion. Maximal density means that there are no vacancies. And in this situation, you can equivalently describe this in terms of tiling of the plane with rhombi in 3 directions. The main diagonals of the rhombi being identified with the 3 types of dimers here. And if you color this rhombi yellow, blue, and red, you can reinterpret this figure here as figures in perspective of a pile of cubes arranged monotonically in the corner of a 3-dimensional box. And the random surface associated with this configuration is the external surface of this monotonic pile of cubes. So not only close packing corresponds to the condition where this correspondence is possible, but is also the only density at which you can hope to have a critical system. So it's well known since the 60s, due to a result of Heilmann and Lieb, that if you have a finite density of vacancies, often called monomers, the system is off-critical. So correlations between dimer here and there decay exponentially. And the only situation where you can have algebraic decay is at close packing. At close packing, you don't necessarily have algebraic decay. So at close packing, you still have parameters you can play with. You can play with the dimer weights, for instance. And if you vary dimer states, you can induce a non-critical phase, say a crystalline phase in this language, where in this interpretation, where dimers are arranged in a regular fashion, which corresponds to a frozen surface here, where the profile is flat and deterministic. Or for appropriate choices of the dimer weights, you can have a liquid phase where correlations between dimers decay algebraically, and correspondingly the random surface corresponding to these dimers has unbounded fluctuations at large scales. And as we will see, these unbounded fluctuations are logarithmic. And what we want to discuss is the universality of this critical liquid or rough phase. So we want to put ourselves in a condition in which the reference solvable model is in a liquid rough phase, and we want to switch on interactions and try to understand what's the fate of the I don't know, scale limit of fluctuations for the height. So this is a particularly interesting question, because the rough phase in many situations is still not well understood. A typical setting where it's not well understood is that of the low temperature phase of the 3-dimensional Ising model, where if you impose appropriate Dobrushin boundary conditions, you can create an interface separating plus and minus phases, and in certain conditions at low temperature you expect to have logarithmic fluctuations of the surface, but there are essentially no results about the properties of fluctuations of the surface. So it's pretty important to develop methods that are robust to control fluctuation properties of random surfaces in the liquid rough phase, even beyond exact solvability. So the specific setting we consider is as follows. So we consider a portion of the square lattice with periodic boundary conditions. We think this portion as consisting of several identical cells of even size m times m. So we repeat these cells many times. In these examples, we have cells of side 4 repeated twice in each direction. And in each cell, we arbitrarily add some non-planar bonds connecting black to white sides. So the model, the graph is bipartite, so you can color black and white the sides. And we add some non-planar bonds connecting arbitrarily within each cell, some black to some white. So in this example, we choose two pairs of black and white, and we connect them with this red non-planar edges. In each cell and in the corridors next to the cells, we assign arbitrarily some positive weights, whatever you like, 1, 3, square root of 2, whatever you like. And after having assigned them, you rescale by lambda. Lambda is a small parameter, the weights of the long edges, so that after the rescaling, the typical weight of the long edges is much smaller than the one of the short ones. So we make the choice in a single cell, and then we repeat periodically over the cells. So this is the definition of the weighted graph on which the dimer model is defined. So here is a recap of the way we proceed. So once again, we choose arbitrary positive numbers, and then we rescale the weights of the non-planar edges by lambda. And if we denote by omega lambda the set of dimer configurations on this non-planar weighted graph, we consider this probability weight for the dimer configurations. So the dependence on lambda, so it's just the product over the occupied edges of the weights. The dependence upon lambda is mediated by this dependence upon lambda of the weights of the long edges. And the goal is to discuss the large-scale properties of the thermodynamic limit of this measure for weights on nearest neighbor edges chosen so that the reference lambda equals 0 measure is in the liquid phase. So once again we start from a planar case. We fix parameters so that we are in the liquid phase, and we switch on this additional weak long non-planar edges. So before I describe the properties we prove on P lambda and on certain specific correlations, let me recall some of the properties of the liquid phase in the lambda equals 0 in the lambda equals 0 case. So at lambda equals 0, there is an exhaustive classification due to Kenyon, Okunkov, and Sheffield of the phases in terms of fluctuation properties of the height. So this is the definition of the height on a portion of square lattice. So the height is defined on the faces of your graph. You choose a favorite face, say the central one, and you fix the height to be 0 there. And then the height on all the other faces are computed using this formula for the height difference between face eta and face psi. So that is the sum over the edges crossed by an arbitrary lattice path going from psi to eta of this linear combination of the characteristic function of having a dimer at E or not. And this weight here, sigma E, is just a sign that is plus or minus 1 depending on whether E, when you is crossed along the path from psi to eta with the white side on the right or on the left. And this definition is well posed in the sense that the right side does not depend on the specific choice of the lattice path, provided this a zero winding over the torus. Next, you look at fluctuations of this height difference with respect to the lambda equals 0 measure. And you say that you are in a frozen phase if the height difference is deterministic. You say that you're in a gaseous phase if the difference is not deterministic, but the variance is bounded uniformly in the distance between the two phases. And you're in a liquid phase on the other hand, the variance is unbounded as you send the distance between eta and psi to infinity. And there is a very simple criterion to establish whether you are in a liquid phase, which is the following. The criterion involves the characteristic polynomial, which is the determinant of the Fourier symbol of the Castellan matrix. The Castellan matrix is a central object that plays a very important role in the exact solution of the lambda equals 0 dimer model. It's a twisted adjacency matrix where the twist is consists of certain appropriate complex phases that must be chosen with a specific rule. So there is a rule to compute this Castellan matrix. You take the Fourier transform, you compute the determinant. This is the characteristic polynomial. And a theorem by Kenyon, Okunkov, and Sheffield says that whatever the weights in your cell, this characteristic polynomial has at most 2 simple zeros. And you are in the liquid phase precisely if this characteristic polynomial has 2 simple zeros. So the set of weights for which you have 2 simple zeros can be written down as an explicit condition easily, and one easily convince oneself that the set is open, non-trivial. You can exhibit many examples of dimer weights for which you are in the liquid phase. And once you are in the liquid phase, you can characterize such a liquid phase in a pretty precise way in terms of asymptotics of dimer correlations and of height fluctuations. So, for instance, if you want to compute the 2-point dimer correlation, so the average of having a dimer at E and another dimer at E prime, this is expressed in terms of the determinant of a submatrix of the inverse Castellan matrix. And the inverse Castellan matrix in infinite volume can be written as the Fourier transform of an appropriate element of the inverse Castellan matrix once you write it in Fourier form. So remember that in the liquid phase, the determinant of k has 2 simple zeros. So the determinant of k to the -1 has 2 simple poles. So the Fourier transform of this function that has 2 simple poles decays at large distances slowly, like 1 over distance. You can compute very explicitly the asymptotics out of the behavior of this function close to the poles. Then you can plug the asymptotics within this formula, and you can, for instance, compute the large distance asymptotics of the truncated dimer-dimer correlations. I write it here for later comparison with the analogous formula at lambda different from 0. So when you compute this, you get a decay at large distances that is like 1 over distance squared. But not only we have a decay like 1 over distance squared, but we have a specific structure. So there are 2 dominant terms colored red and blue here. The red term goes like 1 over the square of this complex linear function, where the coefficients are just the derivatives of the characteristic polynomial at the simple zeros of the characteristic polynomial itself. So this is a complex linear function, and here you take just the standard square. In the blue term, you take the absolute value squared. So here there is a first difference between the 2 terms. And moreover, in the blue term, you have this additional oscillatory term. Then there are additional subleading terms. Okay, so this is a detailed form of the asymptotics of truncated dimer-dimer correlations. And once you have it in your hands, you can plug this into the formula of the covariance for the height difference. So remember that the difference between height at 2 faces is given by sum over a lattice path of certain linear combination of this characteristic function of dimers. So the covariance is written as a double sum over 2 lattice paths of truncated dimer-dimer correlations with appropriate signs in front. So if you deform in a convenient way these paths and you use the asymptotics shown in the previous slide, you can compute the asymptotics. Oh, here there is some there are some errors missing. Sorry. So here there should be a plus subleading terms. So the dominant contribution to the covariance is logarithm involving this complex linear function introduced above. The fact that you get the log is relatively natural from a dimensional point of view. Remember that this decays like 1 over distance squared. You have a double sum over 2 paths. So dimensionally, you get something like a double sum of 1 over distance squared, which gives, roughly speaking, a log. So the log is not itself a surprise. Of course, the specific structure is remarkable. And what is particularly remarkable is the fact that the prefactor here is independent of the choice of the dimer weights. So this is really a remarkable property noticed by Kenyon, Okunkov, and Sheffield, and connected by them with a special algebraic property of the curves separating the frozen region from the liquid one. And so you have a sort of universality property of this stiffness coefficient with respect to the choice of the weights. So this is the formula for the covariance, but you can build upon this and compute higher order moments and prove that after appropriate coarse graining, the height difference converges to a massless Gaussian free field with a Green function that is related to the log of this phi plus. Okay, so this is the structure of the liquid phase at lambda equals 0. So what happens now if we switch on a perturbation? So how is this picture modified? Of course, there are several problems to face. Most important one is that as soon as you switch on lambda, you don't have any exact solution to rely on anymore. Here, notice that you don't even have exact solution in the form of beta ansatz, as it happens to the 6-vertex model close to the free Fermi point. Here, you just break the exact solution. You don't have closed formulas for dimer correlations or height fluctuations. And what you can try to do is to use perturbation theory in lambda. But if you do it naively, this naive perturbation theory will be divergent as the system size goes to infinity. So if you want to use a perturbative approach, you need to use some multi-scale method possibly inspired by the Wilsonian renormalization group ideas. And this is what we do in order to try to answer to the following questions. So about the asymptotics of dimer-dimer correlations at lambda different from 0. So are for instance, the critical exponents the same? Like, so the decay is it like 1 over distance squared, or is it different in the presence of lambda different from 0? And what about height fluctuations? So as I already briefly mentioned, in a non-planar setting, the height is not canonically defined in general. But in our setting, where the non-planarity is restricted to these cells, you can easily define the notion of height, say in these dark gray phases. So you can define the height difference between dark gray phases using lattice paths connecting these dark gray phases along the corridors that don't have any non-planar bridge above. So the notion of height is well defined, and one can ask whether height fluctuations still diverge logarithmically and whether the scale limit is still a massless Gaussian free field. So here is the first result concerning asymptotics of dimer-dimer correlations in a setting where, once again, in the reference lambda equals 0 case, the dimer weights are chosen so to be in a liquid phase. So we are in the liquid phase and we switch on a small lambda, where the smallness condition could depend on the specific choice of the weight. And here is the result. So we have an asymptotic behavior that has a structure that is reminiscent of the one at lambda equals 0, but there are some important differences. So there is again a red and blue term that I would like to compare with the corresponding red and blue terms of the solvable case. The red term has exactly the same structure. It's a linear combination with appropriate coefficients of 1 over the square of this complex linear function with coefficients alpha omega and beta omega that similarly to these other coefficients are all analytic functions of lambda. So at lambda equals 0, alpha, beta, k reduced to those we computed exactly in the lambda equals 0 case, for which there are explicit formulas. Here in general you have analytic modifications of all these parameters. The second term, similar story. There are parameters that depend analytically on lambda. Again, there is an oscillating factor. Here there is a 1 over absolute value of phi to an appropriate power. But now notice that the appropriate power is not 2 anymore. It's 2 times nu, where nu is what we call the anomalous critical exponent. This reduces to 1 when lambda is equal to 0, but in general is an analytic function of lambda, and you can, if you compute explicitly the first Taylor coefficient, you see that generically in the choice of the weights, this is different from 0. So notice in particular that this nu is generically larger or smaller than 1, depending on the sign of lambda. So depending on the sign of lambda, either the red part or the blue part is dominant at large distances. So now once you have this detailed asymptotics for dimer-dimer correlations, you can plug this into the formula of the covariance of the height difference. And if you repeat the strategy used by Kenyon, Okunkov, and Sheffield, you get this result up to additional error terms that I forgot to write. Actually, we get this result with the same function times addressing in front, provided there is a very special relation between the coefficients k of the red term in the previous slide and the coefficients alpha omega and beta omega of this complex linear function phi. So only if there is a special relation between these coefficients, you get this result. Notice that the corresponding relation between these coefficients in the lambda equals 0 case is something you can very easily check explicitly, because there are explicit formulas for all these guys. In the lambda different from 0 case, a priori you only know that these guys are analytic function of lambda with certain very complicated Taylor coefficients, and the relation itself is very difficult to check. Also, if you write down, once again, at first order this A, you realize that in general this is different from 1. So here this prefactor really depends on the choice of the weights, contrary to the lambda equals 0 case. So also in this case, once you get this, you can also get similar formulas for higher order cumulants, and you obtain a result on the scale limit of appropriate coarse graining of the height. So this is a form of our main results on the scale limit of height fluctuation. So fix a smooth, compactly supported function in the plane with 0 average, and compute and use it as a test function against the height function computed on the faces of a rescaled lattice. So you rescale your lattice by epsilon. So after rescaling, the lattice spacing is epsilon rather than 1. You test h against psi, you subtract the average, and you rescale by epsilon squared. So this is the coarse-grained height function associated with psi. You take the characteristic function of this with respect to the infinite volume measure with lambda different from 0, send the epsilon to 0, and you get this Gaussian function with covariance that is -1 over 2 pi squared log of phi plus. So here is the special relation that we need between the alpha, beta, and the coefficients k of the red part of the asymptotics of dimer-dimer correlation. What we actually need is that this expression in square brackets is equal to the opposite of this other expression in square brackets. So it's crucial for this result to hold that these two quantities are one the opposite of the other. And as I already mentioned, this A of lambda depends in general on the weights, contrary to the lambda equals 0 case. However, there is still a special relation which is the following. So this coefficient A is exactly the same as the critical exponent of the blue part of the dimer-dimer correlation. This is a very non-trivial relation that in principle you could think of checking at the level of comparison of Taylor coefficients of these two analytic functions, but if you try to proceed this way, you're just lost. You need to do something more sophisticated than this, and time permitting, I will just comment on what you should do in the last 5 minutes or so. So a few comments on these results. The big part of the technical work is contained in a series of papers by myself, Mastropietro, and Toninelli, where we treated a model of this sort and we discussed similar questions. in a planar dimer model with finite range interactions. By this I mean that the Gibbs measure is not a product measure there, but there is a non-product contribution corresponding to a finite range interaction. Here in this latest work I presented, I would generalize this construction to this weakly non-planar class of dimer models. The A equal nu scaling relation is not the first example of Kadanoff or Haldane scaling relations. We named these scaling relations after Kadanoff or Haldane, who introduced similar scaling relations in related contexts. Not exactly the same one, but very much related. So other examples were proved earlier by Benfatto, Falco, Mastropietro, in particular for Ashkin-Teller 8-vertex and XXZ quantum spin chains. The difference of the results I just presented compared to these earlier ones is that this is the first example of a scaling relation involving critical exponents for a non-local observable like e to the I alpha h epsilon. So non-local observables in the fermionic language, like this vertex operator here, are particularly important in many applications, and it's I mean, among the motivations of this works was exactly to understand the scaling limits of non-local observables of this sort. So the combination of theorems 1 and 2 can be read by saying that at large scales, the height function behaves like a massless Gaussian free field with stiffness A, and the dimer observable behaves like a linear combination of the derivative of the Gaussian free field and of a Vic-ordered version of the complex exponential of the Gaussian free field. So you see that there is, in the scale limit, there is only one fundamental object that controls somehow the behavior of both H and the two different contributions to the dimer observable, in line with the predictions of formal bosonization or Coulomb gas methods that are at the root of the weak universality proposal of Kadanoff. Okay, I will skip this and I will use a couple of minutes more to comment about the strategy of the proof. So as mentioned, at lambda equals 0, the model is solvable with a determinant solution corresponding to a model of free fermions. If you switch on lambda, there is an exact way to map the model into a model of lattice interacting fermions. And this can be treated via multiscale analysis of the same sort used in the starting from the early 80s in the constructive quantum field theory community to study several interacting fermionic quantum field theories. In our setting, the fact that the characteristic polynomial has two simple zeros, exactly two, implies that the fermionic field in terms of which we describe the system has several massive components that have no effect on the large-scale behavior of the system, and just one complex chiral massless component. And the effective theory for this massless component is a lattice regularization of the Lattinger model, which can be studied by multiscale analysis via comparison with an infrared reference model. So the theory of this reference model is due to mainly to Benfatto Mastropietro, and the key point that I already mentioned is the property of vanishing of beta function, which allows to prove for this reference model that the strength of the quartic interaction tends to a finite value at large distances. And once you have this exact cancellation for the reference model, you manage to export it to the dimer model, and this implies the emergence of a non-trivial anomalous exponent nu. Notice that to prove this cancellation at the level of the reference model, you need a lot of quite fancy methods like chiral word identities, Schwinger-Dyson equation, and non-renormalization property of the anomalies. Finally, to prove the scaling relation, you need to compare predictions of the asymptotic chiral word identities of the infrared reference model with certain other exact lattice word identities of the dimer model, which follow from the local conservation law of dimer number at the lattice level. And this comparison implies that A over nu is protected by symmetry, and there is no dressing under the multi-scale procedure. Okay, so a summary. Non-solvable, non-planar dimer models close to their determinantal free Fermi point can be studied via constructive fermionic RG methods. The approach allows us to construct scaling limit of dimer correlations and height fluctuations. Effective interaction is marginal, so control at large distances requires cancellation following from emergent chiral word identities. And universal scale relations follow from comparison of chiral word identities of the reference model with exact lattice word identities of the lattice dimer models. And I think that's essentially all. Here is a list of open problems and perspectives, and thank you very much for your attention.
Yeah, thanks very much, Alessandro, for this beautiful presentation. Let me remind everybody that the questions to Alessandro cannot be posed here on this website, but you have to go to the Discord chat, and there you can pose your questions in writing. I close the session now hereby, and if you're interested, there will be a ground state of Bose gas talk in 15 minutes on a different site. So
thank you.
I'll be seeing you. Thank you, Alessandro. Bye.
Thank you, Volker. Bye.